uniform magnetic field. So this is a uniform magnetic field of a field induction B. So in this, let us assume that a magnetic dipole is placed such that the magnetic moment is making angle theta with the direction of the magnetic field. Now let us say this is south pole and north pole. This is the direction of the magnetic moment and this is the direction of the magnetic field induction. So angle between these two is theta. Whenever a Bohr magnet is placed in a uniform magnetic field having pole strength m each, this is minus m. Why? Because south pole is judged as a negative pole here. So this pole will experience a force. We know that B is equal to force experienced by a unit north pole. So force experienced is equal to mb. So this small m or the plus m will experience a force in the direction of the field. So this is F1. Similarly, the south pole will experience a force in the opposite direction to this one, F2. So here F1 is equal to minus F2. That means the magnitude of these two forces are equal to mb only, but this is acting in the direction of the field, this is acting in the opposite direction of the field. So the net field here is equal to 0. That means whenever a Bohr magnet is placed in a uniform magnetic field, it will not experience any force. That's why it will not have the translatory motion. As the net force is 0, it will not experience any translatory motion. So the magnet will not move along a straight line. But instead what happens, as these two are equal, opposite, parallel, non-collinear forces, they constitute a couple. So this couple will rotate the magnet about its center. So due to this, this force will act like this force will act like this magnet will rotate in the magnetic field. So what is the torque experienced by this one, which is given by R bar cross F bar, or which is also written as RF sin theta. So I am going to write tau is equal to, R is the perpendicular distance between the two forces. So this is the length 2L theta. This is the perpendicular distance R. So I can write sin theta is equal to R by 2L. So R is equal to 2L sin theta. Here in place of R I am writing 2L sin theta into F is equal to mb. Here I am going to write R into F only. Sin theta is not required because I am writing R in terms of this one only, sin theta. So tau is equal to m into 2L will be capital M B sin theta. So this is the torque experienced by a dipole when placed in a uniform magnetic field. Now, when does this torque is maximum, when does torque is minimum? Now, if the dipole is placed parallel to the field, if dipole is placed parallel to the field, then theta will become 0. So dipole is parallel to the field. So sin 0 is 0. So torque will become 0. If dipole is perpendicular to the field, so theta will become 90. So this is perpendicular to field. Then this torque will become mb into sin 90, which is equal to mb only. And then the third case is if theta is equal to 180, theta is equal to 180 degrees, anti-parallel to the field. Now sin 180 is minus 1, and once again the torque will become minus mb. As I said earlier, this is 0 only because sin 180 is 0. And if theta is equal to 270, then also torque will be minus mb. This plus or minus mb is the maximum value of torque, and theta is equal to 0. This torque and this torque are minimum. So torque is minimum if the dipole is parallel or anti-parallel to the field. Here I am writing tau is minimum if Bohr magnet is kept parallel or anti-parallel to the field. Suppose if it is kept perpendicular, either it is 90 or 270, it will experience maximum torque. Now, if I want to rotate this bar magnet in this magnetic field, then I need to do some work. So what is the work done here? Work done to rotate the bar magnet. So do this, I have to multiply torque with angular displacement. If the magnet is moving along a straight line, force into displacement. If magnet is rotating, torque into angular displacement. So dW is given by torque is equal to mb sin theta into d theta. If you want to find out the total work done, integral dW is equal integral mb sin theta into d theta. Here mb is constant, bring it outside. Sin theta d theta will be minus cos theta. This will become mb cos theta. Whatever the work it is done, this will be stored as energy. Here this energy is called magnetic potential energy, which is with the letter U, and this is given by some cases it is given as UM also, because we have electrostatic potential energy also. So magnetic potential energy will be equal to minus mb cos theta. So from the basic principle that we have studied in electrostatics, whenever the potential energy is minimum, the dipole will be in stable equilibrium. So here, when does this will be minimum? Now let me take theta is equal to 0 degrees. That is, the dipole is parallel to the magnetic field. Then this will become U will become minus mb cos 0, which is equal to minus mb. This is the minimum potential energy of the dipole. Similarly, if theta is equal to 90 degrees, that means when the magnet is placed perpendicular to this one, this will become cos 90 0, U will become 0. Suppose if theta is equal to 180 degrees, theta is equal to 180 degrees, potential energy will become mb of cos 180 is minus 1 minus of minus plus. So this will become plus mb. And from these three cases you can see this is the minimum potential energy and this is the maximum potential energy of this one. So whenever the potential energy is minimum, then dipole is said to be in stable equilibrium. In competitive exams, they will ask you to find the condition of stable equilibrium from the given data. So potential energy must be minimum, and it is possible if it is parallel to the magnetic field. Similarly, if the potential energy of a dipole is maximum, then the magnetic dipole or bar magnet is said to be in unstable equilibrium. And this is possible if theta is 180 or anti-parallel to the field. What is the work done to rotate the dipole from one given angle to another given angle? So work done is also equal to the potential energy, difference between potential energy. So work done W is given by PE final minus PE initial. So here I am going to write work done is given by, what is PE final? So PE is equal to minus mb cos theta. So let us say I am rotating this from theta 1 to theta 2. So PE final will be minus mb cos theta 2. This is minus mb cos theta 2 minus initial PE will be theta 1. So this is minus mb cos theta 1. So the work done is given by mb common here, mb cos theta 1 minus cos theta 2. So this is the work done in this case. If a dipole or bar magnet is rotated from the direction of field to the vertical direction, so work done in deflecting a bar magnet from the direction of field to a direction perpendicular to the field. So here work done is given by, our expression is mb cos theta 1 minus cos theta 2. Initially it is in the direction of the field. When the bar magnet is in the direction of the field, theta is 0. So this is cos 0 degrees minus, it is perpendicular to the field. So this is cos 90. So this will be equal to mb into 1 minus 0, which is equal to mb. So this is the work done to rotate the dipole in deflecting dipole from direction of the field to the perpendicular to this field. Similarly, in one more problem, if I wish to rotate this magnet from here to 60 degrees, what is the work done? From theta is equal to 0 degrees to theta is equal to 60 degrees. Work done is given by mb cos 0 minus cos 16, which is cos 0 is 1, cos 60 is 1 by 2, 1 minus 1 by 2. This will be mb by 2. That is exactly half of the work done to rotate this from here to here. Suppose if I wish to rotate the dipole from here to parallel to anti-parallel to the field, in such case, so what is the work done? That is theta 0 to theta 180 degrees. The total work done is equal to mb cos 0 minus cos 180. So work done is given by mb. This is 1 minus of minus 1. This will become 1 minus of minus 1, which is equal to 2 mb. Two power magnets are joined in the form of plus, and it is pivoted at the center, and it is free to rotate in the horizontal magnetic field of field induction BH. This is the horizontal field induction of Earth. Now, when it is in equilibrium, so generally this magnet will try to rotate in this direction due to this one, and this magnet will try to rotate in this direction. So this is the torque experienced by this one, this is the torque in the second magnet. In equilibrium, torque experienced by first bar magnet is equal to torque experienced second bar magnet. What is the torque equation? Which is given by mb sin theta. Here I am going to write this as first one is m1 bh, the angle between this with the horizontal magnetic field, and this one is theta. So I am going to write sin theta, which is equal to m2 bh. And you can see, as these two are perpendicular, this angle will be 90 minus theta. So I am going to write this as sin 90 minus theta. Here BH and BH will cancel. So we can write m1 sin theta is equal m2. This is cos theta sin 90 minus theta. So sin by cos will become sin theta by cos theta will be equal to m2 by m1, and tan theta is equal to m2 by m1. So this is the condition for these two, this system to be in equilibrium in Earth magnetic field. Magnetic needle is lying parallel to a magnetic field. So this is the magnetic field, and the needle is parallel to the magnetic field. That means theta 1 is 0 degrees. Requires W units of work to turn it through an angle 60. So to turn this to an angle 60, we need to do W units of work. The torque needed to maintain this needle in this position, how much torque is required? So first of all, work done is given by mb 1 minus cos theta. So this is equal to mb, because previous it was 0, cos 0 is 1, direct derivative 1, and theta is 60. So this is 1 minus cos 60 degrees. So this is mb into 1 minus half. This is mb by 2 equation 1. So this is the work done to rotate this one from here to here. So after reaching this point, I need to hold it with some torque. So what is the torque in this position? Torque tau is given by mb sin theta in this position. So this is mb sin theta, and theta is given as 60 degrees in the problem itself. So I am going to write this as mb into root 3 by 2. So this is equation 2. Now let me divide these two, torque with W. So tau by W is given by, this is mb root 3 by 2 by, this is mb 1 by 2. Here you can cancel these two and these two. This will become root 3. So the torque required is root 3 times the work done to rotate this dipole to this position. So if work done is W, it is given in the problem. So I need to apply root 3 times the W units of work to keep this one in the same position.